Good morning and welcome to our monthly look at all things networking. Usual team this end, myself, Mike Lees, Product Manager, and Ed Stanier, our Product Specialist. Morning, Ed.
Morning, Mike. Morning, everyone.
So this is the part 2 of our look at IP addressing and subnetting. So Ed, last time we did things a bit differently, didn't we? We kind of dived straight into subnetting rather than building up to it. That's something you convinced me to do. I think you said there was just no way around it. We've got to understand subnetting.
Exactly.
Whether we do it week on, week out, daily, we've got to understand the basics.
Yeah.
And so that's really why I went for it. But today is kind of going back to our usual approach and very much positioning the material and the agenda with the OT engineer in mind. And by an OT engineer, I mean an automation engineer, someone who's not doing networking all the time. It's just part of his job. So we're really talking about end users here. We do get a lot of systems integrators on the call, which is great, and I know they get valuable information from the sessions as well. But this is really all about OT engineers who are faced with doing networking, probably without the background in it. So that's the agenda we put together today, very much going through some of the background almost of the addressing and subnetting. And the troubleshooting, I think, will be interesting as well, Ed, because that's what people come across most, isn't it? Problems on the networks.
Yeah.
Touching on IPv6, and then at the end, the usual questions and things. I've got to break with tradition again, Ed, here. We've only had one question in advance this time, which is a bit unusual, but it's a question very similar to what we had when we were covering VLANs, and it's almost this relationship between subnetting and VLANs. There's definitely a confusion there, and I mention it now because it might help people as we go through today's webinar.
Yeah.
Yeah. I mean, I'm not sure if people are confused. They're going to, a webinar will be a chance to get it over completely. I mean, what do you think?
We can certainly try, yeah. And it's this kind of confusion between VLANs and subnets, the relationship between them, and the differences between them. And I suppose there's no super easy way of explaining it, but really when you're looking at VLANs and designing subnets and IP address schemes, that kind of thing, really you need to be approaching it in the way that you need to be looking at your IP address schemes first and your subnets, because they are what will govern how big your networks are and how many devices you can have in each network. Your VLANs will kind of come on top of that afterwards. You have to imagine that your IP address schemes, we're looking at layer 3, looking at the logical addressing of our clients and our devices. And the VLANs are a layer 2 technology, and VLANs essentially just give us an easy way to distribute our subnets throughout our kind of physical infrastructure. So they are different things, but really you should be, when you are designing them, you should be designing your IP address schemes and subnets first. They are what should have all your consideration. Because they, as I say, they will govern the size of your subnets, how many devices you can have in there. And your VLAN ID has no relevance to your subnet. So, we could create an IP address scheme and we can assign any VLAN ID whatsoever we want to it. There's no direct relationship between the two as such. So if you can kind of bear that in mind as we go through this slide.
I guess we'll touch into trying to help as much as possible, but it's not an easy one.
It's not, no.
IP address classes and ranges, Ed.
Okay. So this table here basically shows us kind of traditional IP address classes. Now, we kind of go through these just to explain how things used to be. And really these classes were designed to kind of give us different size networks. You can see the kind of 5th column, we've got this default subnet mask, and if you can remember from last week, the subnet masks and how that determines how many devices we have in each subnet, you can see here we've got a Class A, a Class B, and a Class C range with varying different subnets, with Class A having the most hosts allowed per network, Class B having second most, and Class C having the least amount. So before the introduction of network address translation and private address schemes and that kind of thing, every device on the internet would have its own public address. Everything would be, we'd have end-to-end point connectivity without any translation services or devices kind of hiding behind a router. So obviously a big organization would need perhaps a Class A range with, a huge amount of address space. Small organization might just need a Class C range with just 254 hosts. Now, it was only a matter of time before we kind of ran out of IP4 addresses, and we had to introduce things like network address translation, so we could have some reserved ranges that we'd use for our local devices. And here they are right here. So we've got 3 different ranges. We've got our 10.00 to 10.255.255.255 range. That gives us obviously the most usable posts there, 16 million. We've got our 172.16 range there, which gives us considerably less. And then finally our 192.168 range, which gives us around 65,000 usable addresses. So when we're now designing our internal networks, we don't look at public addresses. We just don't have those anymore. You'll struggle to even buy a public IP address anymore. Normally, your internet service provider will allocate you a single static one, but it's hard to buy a range. So when we're talking kind of internal addressing and when designing IP address schemes, we want to always use one of these internal ranges here. And then your WAN services will all use your static address or static addresses, given either by your corporate network team or perhaps your internet service provider. So with that in mind, everything is kind of classless nowadays, so we don't get too hung up on Class A, Class B, Class C, that kind of thing. We can use any one of these ranges here, and we can use any mask whatsoever that we want. So we've got a lot of flexibility in which ones that we're going to use. But you just have to remember that these ranges here, they are not publicly routable. That means we can't present these addresses onto the internet, and the only way that devices within these ranges can access the internet is through a public IP address that obviously your WAN provider will assign you.
Okay, and the network address translation, and I know you're quite keen at some point, because that's quite a big subject in its own right, isn't it? So maybe we should look at that at some point in the future.
I think, yeah, we should perhaps dedicate a webinar to that, because it's a reasonably kind of technical heavy protocol, so and there's different types of NAT we can have, so I think we'll dedicate a webinar to that.
So this is about designing IP address schemes, and again, going back to OT engineers, automation engineers, I don't think that they'll generally be designing networks head, but it's almost understanding what they've got, understanding how the design criteria will help them understand whether they've got a good network, anything that's been designed or just thrown together.
Exactly.
Or more likely, what we see is maybe a network started off with a good design,
yes,
and over time has degraded. So
that's
understanding
right.
what goes on in terms of designing a network,
yeah,
I think is a good skill to have.
Absolutely, yeah. So if you ever did find yourself in the shoes of having to, come up with some IP address schemes, or you just want to kind of review what you've already got, I mean, the first question you'd be looking at when you are designing subnets and IP address schemes is you want to see how many different networks you actually need in the first place. There's obviously no limit to how many networks you can have. You've got a huge IP address kind of range to deal with. So you want to kind of make it the most efficient kind of design as possible, making it kind of practical and not causing yourself massive amount of administrative overhead. So really the goal of us creating these different subnets and having different subnets on your network is to start adding some segregation and some security boundaries, and also reducing the size of these broadcast domains. So IP Ethernet works on the kind of principle of broadcast traffic, which allows us to learn MAC addresses from IP addresses. Now you can imagine a large network, there's a lot of this broadcast traffic flying around, and eventually you'll get to a point where your broadcast traffic is consuming a certain chunk of your bandwidth, and that really makes for inefficient networks. Not only that, but also when we start splitting up these broadcast domains, we're starting to add security boundaries. So you want to kind of look at how many different networks do we actually need, and we can kind of start grouping devices together. And really the way that we should be grouping them together is kind of common devices that are constantly communicating with each other. You might have a bunch of PLCs that are constantly talking to each other but don't really talk to much else outside of their PLC range. And that would be the perfect scenario for creating a PLC network. And then the small comms that we do require to a PLCs from, a SCADA server or something like that would be routed through a layer 3 device, a router or a switch. So really you want to start grouping your devices together, and as I say, the best way to approach that is look at devices that are constantly talking to each other, and PLCs are a great kind of start. You know, they're normally in some kind of configuration where they're constantly communicating each other and exchanging values, that kind of thing. And the same could be said for, you know, a server network. Perhaps we've got a SCADA or a Wonderware server estate with application servers, historians, that kind of thing. And again, that would be a good fit for its own network, because also when we're talking about servers, we want to add a kind of layer of security there. So having your servers in an isolated subnet, and we've got some control then over what can and can't access them. Again, that's another good scenario for a different network. Now, obviously, what we don't want to do here is create lots and lots of tiny little networks with just 1 or 2 devices in. There's nothing stopping you from doing that. It's just you've got the administrative overhead. You've got the extra kind of issue when it comes to troubleshooting. You're just adding an extra layer of complexity in there. So really, we don't want our networks to be too big. We don't want them to be too tiny. So there needs to be a little bit of common sense there as well. Which kind of comes on to the next question of how many devices, you know, should we have in each network. And really, there's no kind of real limit to this. Your eventual limit will just come from your hardware and your bandwidth. Obviously, we should apply a little bit of common sense here. We don't want a network of 100,000 devices. A lot of people, a lot of experts in the network industry would kind of recommend, you know, around 1,000 devices or a /22 to be the very maximum recommended amount.
And if people were listening a month ago, they'll know that /22 means 10 bits for the host.
Correct, yes.
This is a 1,024 hosts, less a couple. So that's where 1,000 comes from in that context.
Exactly right,
so,
yeah.
So everybody knows that now.
I would hope so, yes, for those who are listening, yeah. Now, in my opinion, that may be a little bit high. The chances are you won't be coming across networks of such vast sizes anyway. And really, if you can keep your networks to kind of under 300 devices or a /23, then that would be ideal. But chances are that you're going to have networks with much fewer devices. But you shouldn't really limit yourself to your subnet mask. You shouldn't specifically create a smaller mask as possible, because you've got to think about future expansion and that kind of thing. And there's no kind of advantage to limiting yourself to a tiny subnet mask and only allowing a small handful of devices in there. So really, once you've kind of decided how many networks you want, how many devices are going to be in each network, and remember, these networks can be of varying size. You could have one network that's really big, one network that's really small. You can mix and match your subnet masks if you like. That's not a problem. And really, kind of industry best practice is to use the 10 range, and the only reason behind that is because it gives you the largest usable range possible. You've got 16 million addresses at your disposal, and you can subnet them in any way, shape or form that you want. With that being said, the only thing you should consider is that a lot of kind of corporate IT policies will use that 10 range. So you don't want to accidentally start overlapping with corporate. For many reasons. There might be some future connectivity that you need to establish with corporate, and if you've got overlapping ranges, you've got problems, because someone's going to have to start readdressing. Now, with that being said, when we talk about subnet masks and that kind of thing, sometimes it's easier, if we look at that bottom point there on the slide, it's easier to just use multiple /24 ranges. So that would give us, for example, a 10.10.10.0, a 10.10.11.0, a 10.10.12.0. They're nice and easy to remember. They're kind of logical. They're ordered. It makes troubleshooting a little bit easier. You can immediately identify when you see a device. You just look at, obviously, the third octet, and you can say, right, I know that that device is in the 10 range or the 11 range or whatever. And if you're just using your normal masks of 255, 255, 255.0, makes troubleshooting a little bit easier. The only thing you've got to remember there is if you've got a large-ish network of, let's say, over 200 devices, you're going to want a slightly bigger mask than that, because your limit with that mask is 254 usable. So if you've got a network which is kind of bordering on that limit, then you want to have perhaps a /23, and that will give you double the amount. That's 512 M. So just a little summary, always use your internal IP address range. Kind of goes without saying really, but you don't want to start allocating internal devices with external ranges. And I have seen it happen, and it causes you problems later in the future when those devices need internet access. You have to start using the different types of NAT and that kind of thing. So really you want to just use one of those internal ranges, and you've got 3 at your disposal with huge address spaces, and preferably if you can use the 10 range, gives you the most flexibility. Always over-allocate your ranges. Obviously you want to ensure you've got plenty of room for future growth. Don't limit yourself because you've got a massive pool of addresses at your disposal. There's no point purposely limiting yourself. With that being said, don't use really small subnet masks, i.e. 255.0.0.0. That would give you 16 million addresses per subnet. And the only thing that can work against you there is that it can be a bit of a security threat when you've got such a huge amount of devices, addresses within the subnet that can be used. They can be kind of used against you by a malicious user or a hacker or something like that. Technical explanation for that could be perhaps for a future webinar. But yeah, don't use really, really small masks like that. And obviously try to group your devices and areas together, but do avoid lots of tiny little networks of just 2 or 3 devices. And again, a little bit of common sense will go into that. And like I said, there's nothing stopping you from doing that, but you've just got to accept that you're going to have a slightly harder time administering, looking after, and troubleshooting your network. And obviously, just for final summary point, to remember why we do this in the first place and why we subnet things and split our networks up. And it's not only to split these broadcast domains up and make your networks more efficient, but also this layer of security. By creating these different subnets, we create, isolation between our 2 networks. We create a boundary. And if we've got a layer 3 device, in between those boundaries, we've got a place where we can start implementing firewall rules, access control lists, and that kind of thing.
There's nicely onto routing.
Okay. So routing between subnets. So obviously we've got our different subnets. We've got our isolation. That's all good and well. But now we obviously want to start allowing subnets to talk to each other. So devices within a subnet normally, so 2 PLCs within the same subnet, they would talk to each other via layer 2, so via switching. What that basically means is that the device's kind of traffic won't leave a switch. They won't go up to the layer 3 device. They will talk to each other on the same switch. The exception of that is if we're using VLANs. But the point is, we've always got to remember that a device in the subnet will just talk to each other through layer 2. Now, if a device wants to talk to another device that happens to be in a different subnet, the way that it determines that is by looking at its subnet mask. So any device, whether it's a PLC, a HMI, a Windows laptop, when it communicates with another IP address device, it will inspect its subnet mask to determine which network it's in. And obviously, when we looked at subnet masks last week, we saw the kind of mask behind that. So when a device deems the other device to be outside of its network, it will use its default gateway to route that packet. So it relies on its default gateway to get that packet to where it needs to go. It's no longer in its control. It sends it to the layer 3 device, and the layer 3 device then will route the packet to the appropriate network. Now, this default gateway, this can be any device that's capable of doing routing. So, that could be a router, a layer 3 switch, a firewall, or if you were really kind of desperate, then you could use a server or perhaps a workstation with multiple NICs in. Having said that, the most common way and probably the most flexible approach to routing between subnets would be to use a layer 3 switch with VLANs and trunk ports. We'll have a little look at that here. So we've got this little diagram here where we've basically got a layer 3 switch at the top. We've got 3 switches underneath, layer 2 switches, just standard managed switches. And then we've got these virtual LANs underneath in these bubbles. So we've got VLAN 10, VLAN 11, and VLAN 12. Now, what makes this approach so good is that we're no longer constrained by which devices go on which switches. So we can now start mixing and matching. We can have VLAN 10 devices on any of our switches. Same with VLAN 11 and VLAN 12 devices. So we've no longer got these physical constraints that we'd have with like a kind of traditional router based on physical ports. So it gives us a lot of flexibility now for where we're placing devices. And we can easily move devices from one LAN to another by just changing the VLAN allocation on the port. And those black links there represent the trunk links, which basically mean that they will carry traffic from absolutely any VLAN. and the layer 3 switch will identify which VLAN it came from through the VLAN tag, the VLAN ID. It then knows which subnet that VLAN is part of, and it knows the destination address it needs to route it to, and that's how we do routing on a layer 3 switch with VLANs.
And I think what highlights them for me, just looking at that first switch on the left-hand side, different ports and different VLANs.
Yes.
If those devices want to talk to each other, even though they're on the same switch,
yes,
it would have to go through the layer 3 switch.
Exactly. Yeah. That's exactly how it works. Yeah. So even you're right. Even though they're on the same switch, they have to go via the layer 3 switch. Right. And that really is the beauty of VLANs. But we have to imagine that VLANs and subnets, they're different things, they're different technologies, but they work in conjunction with each other. And we should always have a one-to-one relationship, one subnet to one VLAN. But that is probably the most effective and the most flexible way of creating a new network now with multiple subnets by using a layer 3 switch and VLANs and trunk ports.
Okay. So should we take a look at troubleshooting then?
Yes.
And I guess this is what we come across on a weekly basis when we're going out on sites. And
exactly.
I guess we're talking about intermittent problems,
yes.
adding a new device and it's not communicating.
Absolutely, yeah.
You often say to me, I think, make a small change, break a lot of things.
Oh, absolutely, yeah. You know, you can make a tiny change, especially when you're dealing with switches and routers. If you start messing with configs on layer 3 devices, you can render your whole network unusable.
It can be quite scary, can't it?
It can be, yeah. I've seen it
change and bring down the whole network.
It does happen, yeah, quite often. So it's good to kind of have some troubleshooting steps you can follow if you ever do find yourself in that situation. So really, the first thing you want to establish when let's assume you're troubleshooting 2 devices, they can't communicate with each other. First thing you want to check is, are they in the same subnet or not? Because that will determine what your troubleshooting steps are going to be. Now, obviously, we can do that by looking at the IP address and the subnet mask of both devices. You might be lucky enough to just have a nice, easy subnet mask, a standard one of 3255s. And if your first 3 octets are the same for each device, then you know that it's in the same network. If you have more unusual subnet masks, then you've obviously got to apply that maths that we looked at last week, or if you're in a hurry, you can just use an online subnet calculator, put in the values, and it will tell you the address range and that kind of thing. So let's assume that devices are in the same subnet, then we know that this is a switching or a device-side issue. And what we mean by this is, if we're in the same subnet, we don't need to start looking at our layer 3. We don't need to look at default gateways. We don't need to look at any kind of layer 3 stuff in terms of our routing, that kind of thing, because we know that these devices should just be communicating each other just through a switch network. So first thing we're going to do is just ping each other. Can we ping each other? That's your most basic kind of connectivity test between 2 devices. So if you can ping each other, then most likely the issue is at the application layer. So if you can talk to each other via ping, then there's a good chance that we've got an application layer issue here, because there shouldn't be any filtering at this point. Because we're not going through a layer 3 device, there shouldn't be an access control list or firewall that's preventing these 2 devices from talking, unless you've got some layer 2 access control lists. But we're not going to go into that. We're going to assume at this point now, and if you can't ping each other, then you're probably looking at an application layer issue, a SCADA issue, for example. If that's not the case, you can't ping each other, then you should start looking at the switches that both devices are connected to. And if you are using VLANs, then you need to start looking at the VLAN assignments. Make sure both devices are in the same VLAN. If they're not, you're never going to be able to talk between the 2. If they are, then you need to start looking at your trunk ports. And this is assuming if both devices are on a different physical switch. If they are, then that traffic needs to be tagged when it moves across from switch to switch. And the only way that's done is through the trunk port. So you've got to have a look at your trunk ports and check that that VLAN is allowed across it. If we're dealing with Windows-based devices, or if you've got access to an ARP table, then check that. Check for an entry for each device in there. So if connectivity is tried to be established and there's no ARP entry, this suggests that there's no Ethernet connectivity between the 2. So this means a device has done a broadcast and it's asked for the MAC address of that IP address and no one answered. So that suggests to me that you've got some VLAN issues somewhere, because that traffic wasn't properly propagated throughout the network. Local firewalls are a big one. Windows firewall, it will catch people out so many times. So always check that as well. In particular, check that if your network's been set to a public network, then Windows Firewall enforce a really strict set of rules. So check that and disable it and test again. Point 4, check you haven't got duplicate IP addresses. That can happen. And if you check your ARC table and you verify the MAC address, you can say for sure that the entry you've got and the device you're trying to communicate with match up. If they don't match up, you've probably got a duplicate IP address. And it means another device has responded to you with the same IP address and you're actually talking to something else. And then finally, just ensure your subnet masks are uniform across all devices. You can have some weird things happen when you have mismatches. Devices will try and communicate in different ways, and we get into the realms of proxy ARP and things like that. So really just check that they are the same.
Some of these classic inconsistent things that we see. It might only fail once a week. And I'm just going back to my days in sort of a hotline environment, the classic what's changed.
Yes, yes.
The networking thing, people could be adding things to a network that you don't even know about.
Exactly.
But that concept of if something has been working and it's not working now, then
yeah,
it's the classic what's changed.
Exactly, and if you've got some kind of audit trail or you're lucky enough to know what's changed, then yeah, obviously you've got somewhere to start. But I guess in big networks with a lot of contractors around, a lot of stuff going on, especially in kind of shutdown environment, then you can end up with just a bit of a mess.
So I guess it gets more complicated then when we're talking outside of a layer 2.
Potentially, yes. Potentially, yes. Although there's actually less troubleshooting steps here. But we'll just run through these. You've obviously got the added complexity of a layer 3, but the layer 3 device, its task is quite simple when it routes packets from one VLAN to another. But yeah, the first thing we want to do is obviously another ping test. Ping test should be one of your first things that you try, because that just proves your basic connectivity. So again, if you can ping from one VLAN to another, from device to device, chances are you've got an application layer issue again. So your SCADA, your underwear, whatever it is, could be misconfigured. Now that is assuming we don't have a firewall between or some access control lists that are filtering that traffic. So that would be another thing to check. Now let's assume we can't ping each other. We need to check the default gateways and the subnet masks have been configured correctly, because you've got to remember that your two devices now, the only way they can talk to each other is through the default gateway, so that has to be configured correctly. Try pinging your default gateway. If you don't get a reply, you're never going to be able to talk to anything outside of your network, so that's most likely where your problem lies. You've either perhaps misconfigured your default gateway, or your default gateway is off or not been configured correctly. So yeah, no reply would indicate an incorrectly configured gateway, or perhaps some kind of filtering going on that's dropping the packet, or even a VLAN misconfiguration, which comes on to step 3. Ensure that you have allocated your VLAN IDs correctly to each port. And obviously also ensure that if you are in an environment where you're using a layer 3 switch, VLANs and VLAN trunks, ensure that your trunk ports are configured correctly to allow the different VLANs across. Because if they're not, that traffic will never be carried to the default gateway and it will never be routed.
Thanks, Ed. Hopefully people found that useful.
Hopefully, yes. Yes.
Next time. Well, we're just going to take a couple of minutes looking at IPv6, Ed, please. We've come to half an hour, so we're almost up to our allotted. But okay, we do get asked a lot about this. I know we're not really seeing it. It's interesting to get feedback from people on the call over the coming weeks in terms of whether they're seeing it, but it's not really hitting our world yet, is it? Why do you think that is?
I mean, I think IP6 at the moment is a lot more relevant to kind of WAN services, service providers, data centers, network operation centers, that kind of thing. There is practically no motivation for OT engineers or organizations to start readdressing their internal clients to use IP6. There's very, very little advantage to us doing that. The whole point of IP6 was because we'd kind of ran out of IP4 addresses. We've pretty much exhausted all our public addresses. The reason the internet's still working as it is because of network address translation, because of these private ranges. And as long as those private ranges are big enough for us, which, let's face it, they always will be with such a huge address space, there's little motivation for an OT engineer or an organization to start readdressing internal clients and devices. The amount of work involved is absolutely staggering. To imagine reconfiguring a plant from IP4 to 6 everything has to change, all your devices, your software, absolutely everything. So that's, I think, the reason we're not really going to see it. It's not going to be in the timeline for next year or the next 5 years, I don't think. It's going to be a long, long time before we have to worry about IP6. So essentially, yeah, we've exhausted all these IP4 addresses. That's why IP6 was created. We've got a much bigger address space. We've got 128-bit address space now instead of 32, which gives us an absolutely enormous amount of addresses, and more than we could ever possibly use. And because of that, we're never going to run out of IP6 addresses. So obviously, because of that, the thing with IP6 is that due to the use of network address translation, we no longer have this end-to-end connectivity of devices that we used to have on the internet. Now that can give us some benefits in terms of security, but I think the overall vision of the internet was it was never going to work that way, hence IP6. So we'll just have a quick look at the differences. So this is another reason why no one wants to touch IP6, because of just the horrendously looking address that we've got there. So it's denoted now in hexadecimal, just to make life a little bit harder for us, so 0 to F instead of just 0 to 9. That's an example of an IP address there, and as you can see, it's pretty horrendous. You know, trying to remember that when you're pinging a device is just going to be the first nightmare for everyone. So we don't have this concept of subnet masks anymore. They are kind of embedded within the address. So when you configure an IP address, you'll configure your IP6 address and your gateway. You won't configure a mask. Now, we can make that address slightly better by leading zeros can be just represented by colons, and consecutive groups of zeros can be represented by double colons. So that example address above would look like that one below in the second to last point. So it's slightly more manageable, but again, I mean, looking at that, it's very unfamiliar to most people. It's very hard to deal with. It's like dealing with a huge MAC address. And again, it's another reason why IP6 isn't going to be adopted internally anytime soon, because of the added complication we've got of addressing now. And just a final rule when we're looking at this address is that double colons can only be used once. So if we've got obviously multiple bunches of zeros, we can only use these double colons to shorten the address once. But I think most people agree that that is still quite a hard address to get your head around and to start managing.
Okay, thanks, Ed.
And
sorry, I didn't realise.
a few more bits to go through. So some other key differences. IP6 doesn't use broadcasts anymore. So we're fundamentally changing the way that we can communicate with devices over Ethernet. We don't do a broadcast anymore, which is good because IP6 does become a little bit more efficient now. Instead of us asking the entire network who has this MAC address, we use a feature called neighbor discovery, which makes it uses kind of a special multicast address. Makes it a lot more efficient for us to start converting our IP6 addresses to MAC addresses. So that is one of the benefits of IP6. By no means is it good enough reason to start changing, but IP6 does introduce that different way of discovering MAC addresses, and it is more efficient. Another more efficient thing is that you can allocate your addresses manually as before. You can use DHCP version 6, or there's a new feature called stateless auto configuration, and that allows us a much easier way of plugging in a bunch of devices into a network and them automatically assigning addresses to each other and discovering each other. Stops us from having to go around and allocate a static address for each device if we're setting up a lab or if we're just doing some internal testing, something like that. So it makes it a little bit more plug and play. And because of this huge address space, the final point is that we don't need NAT anymore. We've got enough addresses for every single device with a plug in the entire world, a million times over. It really is a staggering amount of addresses. So we no longer need to have internal ranges, that kind of thing.
Because on the face of it, it offers an awful lot, doesn't it, and offers to reduce complexity, but I think you summed it up at the start when you said there's no motivation, there's no business driver for changing.
Exactly, yeah. As I say, the switch over from 4 to 6 would just be a ridiculous amount of work for anyone, and the skill set required as well, because IP6 is still a reasonably new protocol and there's a lot of differences, so there's a certain amount of knowledge required to start looking at that, and it's quite specialist knowledge at the moment. Most people in the networking industry can be very skilled, but there's only a small handful who will be really kind of technically proficient in IP6. again, it will be service providers and people who deal with WAN services rather than, you know, internal networks.
Right. I think that is it now on IPv6.
Okay, that was the final slide. Excellent.
So, yes, questions. I don't think any questions have come in this morning. As you know, we don't make up questions on these webinars. We will go through this one in a moment, the one that was sent through that you touched on at the start. Yeah. But I'm just going to mention what we're planning on covering next time. And the suggestion was networking in virtual environments. I know you're quite keen to do this, Ed.
Yeah, I think that'll be an interesting one. Very relevant as well to OT engineers. You know, virtualization's a big thing nowadays. So there's obviously that element of networking within virtualization. So it'd be good to have a little bit of a techie webinar on that and how it all works.
So we'll send out the invites for that over the next couple of weeks. So this question then, Ed, about the question is, what is the recommended subnet size when using VLANs? And to put it politely, I guess the fact the question is being asked means that there's a misunderstanding of the topic to a certain extent.
Yes, I would agree with that. Because really, there's no recommended subnet size when using VLANs because they're quite different things. And I couldn't recommend a subnet size regardless because your subnet size depends on the number of devices you've got in the network. Let's assume you're always going to have under 200 devices, then I would recommend a subnet size of 255.255.255.0, your most common and standard subnet mask. But really, you know, your VLANs are a different thing. Your VLANs are a layer 2 technology, and they kind of sit underneath your subnets. Your VLANs are just LANs, basically. It's just a LAN, but the virtual bit allows us to distribute this LAN across a bunch of different physical switches. So they're very different things. When you create a VLAN on a switch, you just need to give it an ID and perhaps a name, which is just relevant to the local switch itself. So when you create a VLAN, you don't create a subnet. You create your subnets first, and then you'll assign a VLAN ID to it, essentially.
Yeah. I don't think I've said it in my simplistic world. It helps for me thinking of VLANs just to drop the V.
Exactly, yeah.
VLAN as a LAN.
Just think of it as a LAN, a more flexible and convenient LAN that you can now distribute around your entire kind of network estate.
But we do understand why people get confused between the two.
Absolutely, yeah.
We'll mention the training course in a moment, but it's a lot of people come in with that misconception, or they're confused about VLANs and subnetting.
Absolutely.
Really about getting hands-on.
Yes. And on the training course, obviously, we dedicate, you know, an entire day to switching and VLANs and that kind of thing. So
I guess this is what we do. this is what we like to do. So just a quick mention on the industrial network audits. I would say 8 times out of 10 that this is a great first step in terms of understanding your existing setup of a network. I think we mentioned earlier on that sometimes when networks are put in, they're in great shape, but over time bits are added to them and they do deteriorate. So the network audits that we offer, they're typically 1 to 2 days on site, Ed, and then a write-up. So they're not massive investments. We're talking sort of 3 to 6K, and we do have example reports that we can send out if this is something that you're interested in. The second thing we'd like to mention, as usual, is industrial network training. We've now run several of these. Seem to be developing quite nicely, Ed. Yeah. The cost of these is £1,250 for a 3-day course, and very much the audience in mind is the same as these webinars. It's for OT engineers. We have had systems integrators come on them, and they've enjoyed them. Yeah. We are also looking at maybe putting on a more advanced course that would be suitable for system integrators. The other interesting thing, well, I think it's interesting, we're putting together a pre-qual form, which is basically a list of questions that we can send out, so you can gauge yourself, your level of knowledge, and to see if a training course would be helpful. It might be a bit of fun doing that anyway, so I'll get that ready over the next couple of weeks. Final thing to mention today, we do have some events coming up, as you can see, towards the end of November, very much focused at that's the big topic of cybersecurity. What we found is at SolutionsPT, we've got this rather privileged position where we see an awful lot of installations and what's actually going out there in the market, and it's allowed us to put together this staged approach to cybersecurity. in terms of helping people through a very pragmatic approach. What do you do first? What's the best things to do? So please come along to these events, find out what we're up to. The downside is you'll have to listen to myself again for half an hour or so. So Ed, just remains for me to say thanks very much, and thank you to everyone for joining us today. Hopefully you enjoyed it, and look forward to speaking to you all again in a month's time. Thank you.
Thanks everyone.